Hello everyone, I'm Nicola Turchi speaking from the University of Luxembourg. Thank you for joining me today in my talk at the World Symposium 2020. Today I will speak about a work that I did together with Gilles Bonnet from the University of Bochum and Zachar Kablutko from the University of Münster. And it is about random polytopes that live in high-dimensional Euclidean spaces, and in particular the behavior that their volumes exhibit. Let me start with an easy example, and it is the example of the so-called 0-1 random polytopes. So suppose that you choose n points at random in the following way, which is you just choose independently their coordinates, which are in number d, because say we are in Rd. So each coordinate can be the one or -1 with probability 1/2, and this describes a point that lives on a vertex of a d-dimensional cube. So if you take the convex hull of these such points, you end up with a subset of a d-dimensional cube. Now, if the points are picked with the procedure I described, of course, if you keep picking points, you will eventually pick all of them. And in that case, you will have covered the whole cube. Now, there's an easy way to estimate such quantity, which is known as the coupon collectors problem, which I renamed vertex collector problem in this case because we are collecting vertices instead of coupons. So if you have capital N to be the number of vertices that you need to pick until all of them are picked, then the expected value of such quantity is 2 to the d log 2 to the d. By definition, when you have n such points, you have covered the whole cube, and the ratio between the volume of the convex hull and the volume of the cube is in particular 1. And it is for such number of points. But on the other hand, if you pick a much smaller quantity of points, in particular, say you pick just d plus 1, you end up at most with a tetrahedron, but could be even something flat. So for sure, when the dimension grows to infinity, then the ratio between the volume of your convex hull and the volume of the whole cube goes to 0. So an educated guess is that it maybe exists a certain threshold of the number of points that you have to pick in order to cover the whole volume of the cube. And this is exactly the content of one paper from Dyer, Furedi, and McDermid in '92 that says that if you have a convex hull formed in the way that I just described, its expected volume is almost the whole volume of the cube, as long as the number of points is more than a certain base with the power of the space dimension. So you see the exponential threshold here. If you are above the exponential threshold, you cover everything. If you are below, you don't cover anything. Notice that there's quite a gap here because there's this gap in the base. And this has been generalized in several ways by Dyer, Furedi, McDermid himself, but also by Gatsouras and Yiannopoulos in similar fashion, but always with IID coordinates, and you keep getting this exponential threshold. Things change a lot if instead of getting IID coordinates, you pick the points, for example, uniformly inside the Euclidean ball. This was the case covered by Pivovarov in 2007, and he found out that, in fact, in such case, the threshold becomes super exponential. It's not enough anymore to have just an exponential number of points to cover the volume, but you need at least d to the power d over 2. as you can see in the result that I've written down here. And you can justify this by thinking of the fact that it's more difficult to cover the volume of a body which has curved parts and not just flat parts like a cube. So what we did with my group back in Bochum was to try to generalize this result to bigger classes of distributions still supported in the Bolto. And these are called the beta distributions, which have attracted considerable attention in past recent years. A lot of results have been discovered about them. And you can see that the density is the one that I've written down in the equation. You have this nice radial distribution with this exponent beta that is allowed to be at least -1. As it's written here, it must be strictly bigger than -1, but you can imagine it to be -1, and then in that case, it's just the uniform distribution on the surface of the sphere. And if you now pick endpoints according to such distribution and independently, the resulting convex hull is called a beta polytope. And you can see that I made some simulations just for dimension 2, so let's call them beta polygons. And whereas when beta is low, you covered the ball pretty easily already with a small number of points. When beta is big, and you can see here, for example, I already increased the points to 150, you have a lot of difficulty filling all the gaps of the sphere. You can see already with beta equals 7 and 400 points, still a lot of the volume of the ball is uncovered. So this is just natural that this is reflected in the threshold of our number of points needed to cover the whole volume. And in fact, the result that we obtained back in Bochum with my group and also Yorgos Kasapis, that was guest at the time, is another super exponential threshold, but with this correcting factor beta here in the exponent of the exponential. And you see beta here is allowed to grow as much as it wants. So if beta grows very, very fast, then you need really, really a lot of points to cover the whole ball. Let me add the fact that recently Chakraborty, Kotz, and Vritsu have found a general recipe that tells you the fact that at least for many, many measures that you pick your points with, the exponential regime or sub-exponential regime makes the volume ratio go to 0, and the super exponential regime makes the volume ratio go to 1. So these measures are for like isotropic measures, or as they call them, kappa concave measure in the case of the super exponential regime. So a large class of measures, you can give a general recipe. But you can see there is still a gap here. So we have 0 and 1. What about every other fraction? And this was the main result that I obtained with Gilles and Zachar. It says the following: if now I correct my base a little bit by dividing by a constant 2x, which is fixed in this case, but I keep the exponent, now I lose the epsilon, but the exponent remains d over 2 plus beta, then the ratio of the volumes is e to the minus x. So you can see here, when x is between 0 and infinity, I can cover every number between 0 and 1. And the proof is based on the integral representation of the expected volume of beta polytopes provided by Kabluchko, Temesvari, and Taylor in 2019. And again, in that paper, they have another very interesting relation that connects the volume of the beta polytope to the intrinsic volume of another beta polytope that lives in another Euclidean space with a different parameter beta you can see here in this equation. And thanks to this result, we can also have a corollary that tells you that when you change the number of points in this way, so D now has changed with K, where K is the index of the intrinsic volume, then the ratio between the intrinsic volume of the random polytope and the intrinsic volume of the ball again goes to e to the minus x. There's another interesting corollary, which is for the case beta equals 0, because for the big case b equals 0, you have that the distribution is uniform, and you have this so-called Ephron's identity that relates the expected volume of the polytope with the expected number of vertices. And this allows for a very precise asymptotics for the number of vertices of the zero polytope, so-called, because beta equals 0. And you can see that when the number of points is as in our theorem, then the expected number of vertices of the resulting polytope goes linearly like n times a coefficient that is 1 minus e to the minus x. So I stop here. I leave you with a list of the references that I mentioned in this talk. Of course, there are even more references, but for matter of time, these are the ones that I could mention. I hope that you enjoyed the topic, and I thank you for your attention. Goodbye.